So this is can be called the uh, the Goldstrand schematic eye. Based on the Goldstrand schematic eye. Hello, can you hear my voice? Okay. Okay, so we have now mentioned the second way for measuring the power of the eye according to the Goldstrand schematic eye. There is a scientist or another scientist called Donder. Donder made another form of the eye. It's called reduced eye. So why it is called reduced eye? This is because of actual reduction of number of points, of cardinal points within the Goldstrand schematic eye. So it is based on Goldstrand schematic eye. It is not an actual eye, but it is theoretical eye. So as in Goldstrand schematic eye, the eye was based on the Gaussian and Listing theory that will assume that the eye is a thick lens that's considered of multiple refracting surfaces centered on one axis. So it is called a compound homocentric system. But in case of Donder assumed that the eye has only one refracting surface and one eye, or one medium. So instead of having the cornea and the lens, the Donder say, okay, we will consider that these two surfaces are one surface. And instead of having an aqueous and vitreous, we will say that this is only one medium. So he replaced all the surfaces and the media of the eye by one curved surface. So since we have only one curved surface, it will have one nodal point and one principal point and two focal points in front of this curved surface and behind this curved surface. So these are the main difference between the Donder's reduced eye and the Goldstrand eye. So the here will be the curved surface, or we assume, or the Donders made his calculations so that he can assume that the eye is made of one refracting surface that's present 2 millimeters behind the anterior corneal surface. And the intersection between this curved surface and the axis or the principal plane will be called the P, or the principal point. This principal point is located in the aqueous. It is 2 millimeters behind the anterior surface. The nodal point will be one nodal point, and it is present 5.6 millimeters behind the principal point, or 7.6 millimeters behind the anterior corneal surface. So this will be the principal point and the nodal point. The refractive indices in front and behind will be the air will be 1, and the medium behind the principal point will be the refractive index of 1.33. And for the focal length, we have the f1 and the f2 as usual. So the f1 will be situated minus 17 millimeters, and this will be equal to the minus 15 millimeters from the anterior corneal surface to the f1, plus the 2 millimeters, which is the distance from the anterior corneal surface to the principal point. So in the exam, note that this is a very common area of confusion. That is when it is asked according to the Donder's reduced eye, the f1 is calculated or equal, is it 15 or 17? So you should notice whether it is calculated from the principal point or it is calculated from the anterior corneal surface. Then we have the f2. In the f2, we have in the f2 is located 22.6 millimeters from the principal point, and if we want to calculate it from the anterior corneal surface, we need again to add the 2 millimeter value. So the f2 will be again 24.6 millimeter from the anterior corneal surface, which will be the same like the Goldstrand schematic eye. So the difference here, again, to summarize, the Donder's reduced eye treats the eye as if it is a single refracting element, consists of an ideal surface, ideal spherical surface separating two refractive mediums. Each one has, or the first one has a refractive index of 1, which is the air, and the next one behind this refracting surface has a refractive index of 1.3. This will be the refractive index of the aqueous and vitreous. So since it has a curvature, then it should have a radius of curvature. So the radius of curvature of this single refracting element will be 5.7 millimeter, which is not the radius of curvature of any of the cornea or lens theoretical eye. The principal point lies about 2 millimeter behind the anterior corneal surface in the anterior chamber. So when the Donders made this reduced eye, he found out when he made his calculations that the power of the eye will be equal plus 60 diopters. So while Goldstrand found out that according to his schematic eye, that the power of the eye is plus 58.6 diopters. So you can find that the difference is very minimal. That's why, since the reduced schematic eye of Donder is much more simple, that's the basics or the basis of all our optical corrections and the optical diagrams that we use in the human eye. So to summarize, we in order to discover the errors of refraction and how to correct, we use the Donder's reduced eye, in which we have a in which we assume that the eye has a single refracting surface that has a f1 anteriorly and has an f2 posteriorly, and it has a nodal point behind this principal point. So the posterior focal distance is about 22.6 millimeters, which is the length measured from the principal point. If we measure from the anterior corneal surface, it will be equal to 24.13 millimeters, which will be the average axial length of the eye. So this is important, that the f2 is located on the retina, which is about 22.6 millimeters behind the principal point, or 24.6 millimeters behind the anterior corneal surface. The nodal point is 5.6 millimeters from the behind the principal point, or it is 7 millimeters behind the anterior corneal surface. Again, the nodal point here is 5.6 millimeters behind the principal point, or it is 7 millimeters behind the anterior corneal surface. So to summarize the difference between the schematic eye of Goldstrand and the reduced eye of Donder, the Goldstrand schematic eye has two principal points located in the aqueous, two nodal points straddle the posterior lens surface, and has f1 and f2, f1 in front of the cornea and f2 located on the retina. While the Donder's reduced eye, it has reduced these values into one principal point and one nodal point and two focal points, f1 in front of the cornea again and f2 at the retina. So here now we know that how can we calculate the power of the eye by using different methods, either by calculation of each power separately or by Goldstrand schematic eye that is based on the principle of Gauss and Listing theory, and by using the Donder's reduced eye. So what is the application of this? What is one of the applications of Donder's reduced eye and is the calculation of the retinal image size. So not only we can know the dioptric power of the eye by using these formulas, but also we can know if we have an object in front of the eye and we know the size of this object, we can know what is the size of its image on the retina. So by using the Dunder's reduced eye, and we have an object in front of the eye. So this is the principal axis, and this is the nodal point. If we have an object termed O in front of the eye that form an image termed I on the retina, and we know the distance of the object from the retina or from the eye, we can know the image size. So how can we do this? This is again by knowing the object size, and the O is object size, I is the image size, and here we have U. So U is the distance of object from the nodal point from here. So how can we calculate it? So we know that the object distance from the eye, or we can calculate it, and we can know the distance from the anterior corneal surface to the nodal point, and this can be given from the Dunder's reduced eye, which will be equal to the 5 millimeters, which is the distance from the nodal point to the principal point here, and 2 millimeters, which is the distance from the principal point to the anterior corneal surface. So we can now know the value U, or the object distance from the nodal point, by knowing the distance of the object from the eye, and add to it the distance, or the distance between the nodal point and the anterior corneal surface. And also we can measure the V, or the distance of the image, or the distance of the retinal image from the nodal point. And this can be also obtained from the Dunder's reduced eye, which is equal 17 millimeters. So the image distance will be calculated from the nodal point to the F2, which will be equal 17 millimeters. The object size can be determined by the distance of the object from the eye, and add to it 7 millimeters, which is the 2 millimeters from the anterior corneal surface to the principal point, and 5.6 millimeters, which is the distance between the principal point to the nodal point. So one of the main basic rules that we learned in our early lectures is the magnification rule, which is the object size over the image size will be equal to the distance of the object divided over the distance of the image. So if we want to know the image size, we should multiply the distance of the image multiplied by the object size divided by the U, which is the object distance. So since we have now the V, which is 17 millimeters, and we have the object size, and we have the U, which is the 7 millimeters, we can now calculate the retinal image size. So the practical application of this is when we want to know the measurement of the visual field effects. So visual field effect, or a scotoma, meaning that there is an area in the visual field that is blind, that we cannot see. So if we have a device that can present a different object, and this object of known size, or O, is known, and it is placed in front of the eye by a measured distance, and we know that the distance of the object in front of the eye, so we know U. So since we know the V, now we can know how much of the retina is affected and how much of the retina is diseased, and you cannot see this object. And this is the principle of the visual field, or the perimetry. So by perimetry, we are placing the patient in front of in a device, has a bowel. This bowel project a stimulus. This stimulus of known size that is presented to the eye. So we know the object size, and we know the distance of the object, and from the Dunder's reduced eye, we know that the distance of the image, or the distance of retinal image size, so we can know how much of the retina is affected, or the image size of the retinal disease. So this is the first part of the first lecture. Is everything clear up till now? Okay, let's now come to the interesting part.